So Norne, it's a synthetic simulation model that was released by NTNU. Again, I'm not quite sure what's let's say the license associated to the release of the dataset, but it's available through OPM. And what I'm going to do is open that simulation file. So the first time that you download the data, you will realize that you will only have the model here without any simulation results. So you have to go through a process of running the actual simulation model yourself. And I'm going to do it. I'm going to just give it a go because I want you to see how long it's actually going to take for this model to run. So let's go into that folder. It's my unit that is mounted into the PE Python folder, Reservoir simulation, and Norne session. And then OPM dash data, and again Norne, quite long path. Okay, so if I list the files here, I can see my simulation model, Norne simulation model there. So if I type flow, that's it. That's all the process. So this model takes about 20 minutes to run. So I'm not going to let you wait for the 20 minutes. I'm just going to go straight and paste some of the results in the folder, and let's start to play with some of the results, right? So let me open just another window. And I have the model already run in my machine. Just going to replace all these simulation cases. If I'm going to try again. Hold on a second. It's hanging there probably. Oh, I see what's going on. Okay. I also have, if we go back to the slides, let me remember more or less the sequence. So let's have a look at the model. The model is actually quite interesting for a model that runs in 20 minutes. We can do a lot of things with it. Structurally, it's quite, let's say, complex, medium complexity, and it has at least 30 layers with a lot of heterogeneity on the model. So let's have a look a bit of at those properties. I'm going to also copy a ResInsight project that I have available for. So, okay, let me open ResInsight. And for those that are not aware of ResInsight, this is a visualization tool for reservoir simulation models, also developed by the same research institute or the entity that it's developing OPM, initially founded by Syntef and Equinor. Yeah, the formats of the files are exactly as the format generated by Eclipse. So you can load it into other commercial tools. So this is a summary spec, unified summary, the restart file. And actually, if we briefly have a look at the model, it's pretty much the same format of Eclipse format with the run spec section. So this is a dimension of the model, and this is oil, water, gas, black oil model with gas is all gas and vaporized oil. And I think one of the features that I can mention from what I can see on the model is that you have quite a few permeability modifiers, especially on the set, representing the KVKH values in every one of the zones. Quite a few field-wide barriers, mean per volume multipliers, and so on. And this is what I was talking about previously about tracers. So yes, there are tracers defined in the model. I don't know if you can actually request the tracers as such. I haven't seen it. Ankit mentioned that apparently it's available. And let's explore a bit more, but there are also, this is in pretty much in history mode, and this is what we're going to take advantage on this exercise. So we have a VLP tables as well for pretty much all the wells, and some network facilities that I haven't really had a look into it in detail. But you can have a look and also let me know if you want to do something interesting with it. We can create something. So if I open this file now, I think I have a project already prepared. Okay, so here we have the way I can probably, let me show you first the static properties here on this project. So if I go into the static properties, it has quite a few equilibration regions, just as at least 1, 2, 3, 4, 5 equilibration regions, as you can see here. The number of active cells is about 44,000 cells. And you also have, if we have a look at the PVT regions, we only have one PVT and one saturation function. However, there are some endpoint modifications for the critical water saturation, minimum water saturation. So there is a bit of an endpoint scaling going on the model, and also for the maximum gas saturation, I think I've seen some sort of endpoint scaling for the maximum gas saturation around the model. There you have a porosity distribution. As I mentioned, it's a bit heterogeneous, the model, and permeability distribution quite a bit range from very high strict high permeability zones, especially on this area, in some of those zones in the model. There are three main areas or three main zones in the model, which are or four. Yeah, the top one. There seems to be a complete barrier at the top of the model, which divides these four zones. And this is a fluid in place reporting region that I have in place for the model. In terms of the wells, quite a few of the wells are, let's go into the dynamics. So if we go into a ternary, as you can see, there is a gas cap initially in the model with an oil rim and an aquifer, or at least a volume representing an aquifer. I don't think there is an analytical aquifer as such in the model. And if we run this forward, you can see that there are not only three, but there are many more wells that are coming in place. They have quite a few injectors like this F1, F2, F4 wells, and slowly you can see the depletion of the model as the time goes forward. Right. So what else we can say about it? So if we have a look at what we have in the model, let me stop this. Yes. So if we have a look at the model itself in terms of summary results, let's have a look at the well, some of those wells. And there is no bottom hole pressure on observed bottom hole pressure on the model. So if I turn these two, you can see that there is the red line, it's observed bottom hole pressure. So it's nothing being measured as bottom hole pressure. However, we have for objective function purposes, which we're going to cover in a bit, we have, as you can imagine, the water oil ratio, the water oil production, the well oil production rate, and we have the water cut for each of the wells. And if I scroll across some of the wells, you can see that this is the purpose of the models was almost to illustrate that the model, as the initial model provided, is not a perfect model, and it can actually be fine-tuned for the purpose of history matching. So taking that into consideration, so we're going to try to use a bit of experimental design, sensitivity analysis, calculate objective function, and then understand some of these wells, what's affecting the quality of a history matching in some of those wells. So there you have, some wells have a very nice match, some others they are not as good as you can see on this one. So the red one is a historical performance, and which I think in this case they have produced using a reference model with certain property distribution, certain fault connectivity, and stratigraphical connectivity or vertical connectivity in the model. And they have provided a base case that it's probably a bit distant from that initial reference case, because this is a synthetic model. But it's quite good model to play with. So that's what we have in terms of the model.